organizing this workshop and for the invitation to speak here. So I guess everything I'm going to say is joint work in progress with Ashwin Iyengar. And the specific results I want to talk about are maybe, let's say, motivated by recent developments in the theory of eigenvarieties. But maybe you're not like directly about eigenvarieties. So so this is still in the morning of the first day. I want to start by talking about the background for the problem I eventually want to talk about. And so I want to say something about what an epsilon isomorphism conjecture is and where it comes from. And epsilon isomorphism conjectures really, I think of as something that come out of the world of special value conjectures and stuff that goes by the names like, equivariant Tamagoa number conjecture and so forth. And so philosophically, so given a very general arithmetic geometric situation, so whatever your favorite framework for thinking about motives is, and, for the purposes of this talk, a collection of Galois representations is perfectly good. So maybe your favorite elliptic curve. What do we expect? We expect to have L functions, as in David's talk. And well, okay, so it should have a meromorphic, it should be a meromorphic function on the complex plane. It should have a functional equation. And its special values should encode the arithmetic of this motive. Okay, so maybe the first L function we learned about is Riemann zeta function or Dirichlet L function. But beyond that, you have the world of the we have an operator over Q, and then define an L function as the product of local factors. And this is holomorphic. And in terms of special values, the BSD conjecture predicts that the special value should tell you, for example, what the rank of the Mordell May group. But the functional equation has the form, well, the L function at S should be related to the L function at 2 minus S, depending on how you've set up the normalization. And you have to throw in some gamma factors at infinity, and you have, crucially, epsilon factor here. BSD conjecture. So something I want to emphasize about this situation is that these local factors, LPES, are defined in terms of determinants of operators on some cohomology groups of E. Okay, so this is great, but you look at this conjecture and you say, well, I want to know about the special values, but oftentimes I really want a formulation of a conjecture which is somehow more categorical. I want coefficients because a motive might come with endomorphisms. I want to consider, congruences between motives. So for example, if I want to construct something over an eigenvariety, I know that I have some construction at, classical motivic points, and I want to know how they vary. And also I frequently want to incorporate twists of Galois representations into my conjecture. So I want something that's really I want a formulation of a conjecture that has more structure than just saying an order of vanishing is equal to some rank. And if, I said that these local L factors were defined in terms of determinants on cohomology groups. If it were just a single cohomology group, I would say, well, okay, so maybe what I'm really looking for is a module, and I'm looking for some description of the top degree exterior product of that cohomology group. But because there are multiple cohomology groups, it turns out that you have to talk about determinants of complexes, rather than just determinants of operators in a single module. So we're going to fix a ring A. For me, A will always be a standard commutative ring. In some formulations of this theory, you want to allow non-commutative rings, but not in this talk. So I'm going to define I'm going to define a determinant functor on, it's going to be something I'm going to define on the unperfect complexes. And it's going to be given by if I take P to be a projective A module of P, I know what this should be. This should be the top exterior power of P. But I'm also going to keep track of the rank that P started out at. So I'm going to consider the pair of this exterior product together with the rank. And given complex, what am I going to do? I'm going to take this to be well, I want to take an alternating power, an alternating product of the top degree exterior powers. And I want to take the alternating sum of note, there's a box operator on these pairs given by
What functor is this category landing in?
Sorry,
what category is this functor landing in?
I'm being deliberately vague about this point, but it's because so the treatment I'm following is the treatment given by Knudsen and Mumford, where this is going to be graded line bundles on A. There are more general formulations which you have to use if, for example, you want to pass the non-commutative case. But Maybe this is good enough. And the unit for this operation is 0, so the trivial line bundle, and 0 the grading, and it has an inverse, so that the determinant, the inverse of the determinant is going to be take the inverse line bundle and then minus the rank. And you extend this, you would extend this to complexes in a natural way. Okay, so why is this a good thing to do? And ultimately the answer is because it lets us talk about special values in a kind of more categorical way. So, so let's say I'm given an isomorphism of 2 modules of the same rank. These are both projective modules. And then when I take the determinant, this gives me a complex Q. And so this is going to be P is going to be of degree 0, P of degree 1. And this differential is going to be this map phi. Well, by definition, this is determinant of P box times the determinant of Q inverse, because there's a -1 here. Okay, so these P and Q are isomorphic. So obviously this box time is going to give me the unit object in some way. But the question is, how is it going to give me that unit object? Well, I can take the determinant of the map, and this gives me a map to that Q box times that Q inverse. And this is canonically isomorphic to this unit object. So I should have called this boldface 1A. And so we've got an isomorphism between the determinant of the complex and this unit object, and it depends on the map. Now let's say that A is ZP, so all modules are Fourier toward all finite modules are Fourier toward them. And let's say we've got map P to Q to H, where H is torsion. So this is a presentation of a finite group H. Maybe this was the wrong word to erase, but it's too late now. Okay, so then determinant of H. Okay, so what is this going to be? This is going to be the determinant of the complex PQ, because H is quasi-isomorphic to this complex. So now this is in degree 0, and this is in degree 1. And so again, this is determinant of P inverse, determinant of Q. And now we have a map from that Q inverse box times that Q, which again is canonically the trivial object. So this map from P to Q is no longer an isomorphism, but the determinant of its co-kernel is trivialized by the unit object, by a map that depends on the map phi. This depends on its presentation. So viewed as a lattice inside QP. I invert P, and then I know that H vanishes. So again, this had better be a trivial object. But how is it trivial? How is it trivial depends on its presentation and given by this map. So how do I want to formulate that? I want to say that this determinant is the ZP lattice generated by the inverse of the determinant as an element of QP. Okay, so I unfortunately erased my previous comments, but the point is that if we're viewing L functions as products of determinants of operators in cohomology, we're saying that we can use this formalism of determinants to say that the special values should be given by trivializations of the determinants of the appropriate Galois cohomology complex. And to say make that precise, we have to know things like Galois cohomology is a perfect complex, and so there is this presentation in terms of finite productive modules. But we know that. Okay, so then we have. I'll write down a sample conjecture. And there are a lot of names attached to these flavors of conjectures. So, for example, Blocado, Fontaine, Ryu. Cado's name should probably be here. But I just want to write down a sample conjecture, which is that there is what's called a zeta isomorphism. Zeta ZP from trivial object to the determinant of a complex that has to do with Galois cohomology. So we'll take U to be spec Z minus some finite set of places. E is again going to be an elliptic curve. Which encodes the special values LE1. And again, this value is supposed to have to do with things like the Mordell V rank, as well as the order of the Tate-Shafarevich group, various regulators. But that should all be packaged together by this isomorphism.
It's the leading term in general, not just LE1.
Sorry?
It is the leading term in general.
Yeah, but it should encode the L value in particular. So I'm being fairly impressionistic about this, but the point is that just as we can determinants of complexes tell us about sizes of person groups, determinants of Galois cohomology should tell us about special value conjectures. So there are both local and global versions of these sorts of conjectures. And having given a kind of a motivational story in terms of global Galois cohomology, I'm mostly going to now switch to the local story. So before I do that, what should an epsilon isomorphism be? Again, impressionistically, the statement should be combine these zeta isomorphisms, these zeta isomorphism conjectures with functional equations. The functional equation for an L function should somehow come from Poincare duality in the appropriate Galois cohomology, and if you do sufficient cancellation and assume enough standard conjectures, you wind up with a conjecture about what should the epsilon factor in the functional equation correspond to. Okay, so that would be kind of a global motivation, but now I want to switch to the local story. So now I'm going to say, let's say I'm given a pair and M. And so these are going to be the coefficients. And this is going to be in some versions of the story, a Galois representation. Later on in this talk, this is going to be a phi gamma module. I'm going to define a graded invertible module should be a lambda module delta lambda m, which is going to be called the fundamental line.
Rebecca,
Uh-huh.
would you mind lifting up that board so it's a bit easier to see what's at the bottom?
Okay, I didn't want to cut off anything at the top, but
Well, maybe swapping the boards, is that?
sure, you do that. So, and now there's a conjecture as formulated by Fukaya and Kato about saying that essentially, however we're defining this fundamental line, it should really encode the epsilon factor of that we expect. Unique lambda linear isomorphism epsilon of m again from the trivial object over lambda to this fundamental line. And this is uniqueness is quantified over all pairs lambda m such that there are a number of natural conditions. I said we wanted to turn special value conjectures and epsilon factors into statements about determinant because we wanted functoriality. So we definitely want this to be functorial in the coefficients. We want this to be multiplicative in exact sequences or distinguished triangles. We want this to be compatible with duality. And to pin it down uniquely, we have to make the observation that in the case where our representation is, say, a lattice in a de Rham representation, so there's an associated Bellovin representation, and in that case, Deline told us how to write down an epsilon factor. And we want this this conjecture to be compatible. We want the isomorphism we're constructing to be compatible with that. There's also dependence on a basis for the Tate twist ZP1 and a description of how this construction changes as you vary that basis, but I'm not going to write that down.
Data basis of ZP1.
Yeah, exactly. Yeah, exactly. So there is also a dependence on that basis, but I'm not going to write it down. Okay, but something I want to observe here is that for Kai and Kato, well, I said that lambda is the coefficients. What kind of coefficients are they allowing? They're going to allow lambda to be an Noetherian semi-local ring, which is if M is the maximal ideal of lambda, we want this to be complete. So, the canonical example is, of course, lambda to be ZP, which is p-adically complete. So I said we also wanted this conjecture to encompass twists by, for example, characters. We want lambda to include, for example, Iwasawa algebras, and if we permit, our coefficients be Iwasawa algebras, that will let us specialize to incorporate twists into the theory. So making a construction over an Iwasawa algebra lets you specialize at either the trivial character or a non-trivial character, and then this will say something about twists.
So M lambda is what, the intersection of the finitely many maximal ideals or something. You can't say the maximal ideal in a semi-local ring.
Yeah, okay, fine. Yeah, sorry. Each factor will be max adequately complete. So if you're happier, I'll just write the local ring to remove the ambiguity from the board. Thank you. Oh yeah, so I think extra condition so that the residue field or project residue fields is finite of p-power order. But in particular for Kai and Kato, this was really an internal conjecture. And so the compatibility with the geometric case is in the case where you're really a lattice. And okay, so how do they define their fundamental line? In this case, well, it's going to be a first factor, which is going to be the determinant of continuous local Galois cohomology. And a second factor, I'm not going to write down precisely because later on it's going to be much simpler. But this is going to be approximately the determinant of the representation together with rank. And then the fundamental line is going to be their product. And so they gave a proof in the rank 1 case.
That one piece and this conjecture are both due to copy.
Okay. Thank you. So more recently, Nakamura said that, well, instead of considering families of Galois representations with integral coefficients, we can consider also pseudo-apnoid families of the gamma modules. So phi gamma modules, as in David's talk, are going to be an enlargement of the category of Galois representations. And one of the, again, as in David's talk, one of the phenomena we see in the category of phi gamma modules is that representations which are irreducible as representations often become reducible as phi gamma modules. And so Nakamura again gave a proof in the rank 1 case. And therefore a proof in the triangulum case, where the case where a representation becomes an extension of rank 1 object. So the most reducible but not split case.
What's the sort of what's the hard thing to prove? I guess there are a bunch of requirements on this functor. Is it there's compatibility with these?
That's certainly a lot of the work here. Yeah, but again, like you look at this determinant, you say this is obviously trivial. The question is, how is it trivial? Because exactly what the trivializing isomorphism should be to pin down to be compatible with Deline's construction is exactly like how is it trivial is exactly the animating issue. Have you written down the right trivialization? And so what I want to talk about in this talk is I want to talk about how to extend this formulation to families over pseudo-apnoid algebras. I guess something else I should add is that when Nakamura reformulated this in terms of apnoid families, you have to add in an additional description of the punctoriality and coefficients to justify passing from, say, an integral family to an apnoid family, given such a map. So so before I go on, are there any questions about either the motivation or the setup?
When you say proof in rank 1 or triangular case, I mean, like it depends on the definition or construction of this fundamental line. Is it just kind of the same definition you gave before? Up to the second factor, the second one maybe needs to be a bit modified.
There is so one of the advantages of working with phi gamma modules is that we're going to have a very concrete description of what cohomology, how to compute Galois cohomology, which in terms of a complex that was originally written down by Hare, and it is compatible with Galois cohomology in the case where you're coming from Galois cohomology.
And for the second ingredient, you just take kind of the classification of rank 1 phi gamma modules against the bundle. Or...
And yes, so you do have to check if those are compatible. So that's one issue that Nakamura ran into when reformulating this conjecture. Okay, so why do I want to talk about extending this to pseudo-apnoid families? So the motivation for considering pseudo-apnoid families, I think, really comes from more recent work in the theory of eigenvarieties. So the eigencurve and various eigenvarieties, they were originally constructed as characteristic zero rigid analytic spaces. But they're also a setting where, as in David's talk, we really want we want arithmetically interesting objects to vary over them. And then, several years ago now, Andreatta Jovica Filoni extended this construction to a mixed characteristic. As a pseudo-rigid space. So pseudo-rigid spaces are going to be adic spaces which behave quite similarly to classical rigid analytic spaces, but which can incorporate points in multiple characteristics. And this construction was extended by a number of people, for example, separately, Galata and Johans and Newton. So the kind of spaces we see now are the space associated to, well, you take power series ring, you consider convergent power series in the variable P over U, and you invert U. So that now this is a ring with, it does not contain a field. It does not live over any field, but it does have this element U, which defines the topology. And so what does this correspond to? So this corresponds to this corresponds to this half-open annulus together with kind of a compactification into mixed characteristic. And the point, the original motivation for this construction was that Coleman had made some conjectures that said the behavior of the eigencurve near the boundary of weight space should really be explained by some characters, by this compactification to characteristic P, which should sort of emanate into characteristic 0. And so what they did was construct this characteristic P compactification. And this characteristic P compactification is going to carry a family of Galois representations. And this family of Galois representations is triangular. So in characteristic 0, well, this was originally an observation of Kiston, and then it was kind of souped up by like, separate work of Liu and Pasha Xiao in characteristic 0, and then at the boundary points, this is separate work of myself and Karnataki Liu, kind of taking the limit into characteristic P. To extend the theory of phi gamma modules into for these sort of mixed characteristic algebras, and then even more recently, Ashwin and Yengar started extending some of these p-adically varying objects to the boundary. So he wrote down a conjectural two-variable p-adic L function over these extended eigencurves. Okay, so if we have it, if we expect a p-adic L function, we also expect to have functional equation. And so we expect to see epsilon isomorphisms working in this sort of mixed characteristic situation. And so this is the this is sort of local epsilon isomorphism that we can in fact write down. I guess maybe I should say that we're still writing this up. Pseudo affinoid algebra A, and so this is going to hold for rank 1 phi gamma modules over QP. It's going to be of character type. It's going to exist a trivialization of the appropriate fundamental line. Compatible with this instruction. So in this statement, delta is going to be a character on the units of QP valued in the units of A. Up to twisting by a line bundle on A, that describes all rank 1 phi gamma modules.
Characterization.
Yeah. Yeah, the space of characters, such characters as smooth, and so we can deform into characteristic 0 to see, and then Nakamura's uniqueness will give us uniqueness in characteristic P. So maybe before I go on talk about the strategy for the proof, I should say that one of the nice things about Nakamura's construction is that because there are Galois representations which are irreducible, of rank greater than 1, and also non-crystalline, Nakamura's construction gave us access to a family of irreducible representations that weren't covered by either previous work on epsilon isomorphisms or Deligne's construction. And similarly, once we prove this, we have access to an epsilon isomorphism for irreducible representations in characteristic P, which are not mod P. So that's one of the nice consequences of having such triangular constructions. Okay, so any more questions before I say something about the strategy? Okay. So the strategy, in every paper on epsilon isomorphisms I'm aware of, the strategy is to pass to a p-adic Lie extension. So so there are previous papers by, for example, Benoit and J, and Ruther, Benikov, Davis. We're going to pass to a p-adic Lie extension. Over QP, and so this is going to have Galois group gamma. And the point of passing to such an extension is that we want the Galois cohomologies to become simpler. And then if you can construct an epsilon isomorphism with coefficients in, for example, the appropriate Iwasawa algebra, or for us, it's going to be, well, I'm going to call it A gamma rig, which is essentially the generic the fiber product of this Iwasawa algebra with A. So if you're writing P, this would be the Briggs analytic generic fiber of the Iwasawa algebra. And then specialize to maybe your original situation or a twist of your original situation. So for us, gamma is going to correspond to going to be a cyclotomic extension, and so gamma is going to be the isomorphic to the units of ZP. So the gamma modules are going to be projective rank D modules over what I've been calling the Roberine writing script RA, and that's the ring of functions in pi, some variable pi, which converge on some annulus. Like 1 minus epsilon is going to be less than or equal to the absolute value of pi is less than. And given such an M, which is the P gamma module, we're going to pass to this p-adic Lie extension by taking the universal deformation over this extension. So precisely, we'll be pulling M back to over ZP to the Iwasawa algebra, which is going to involve inverting U, because M is over A, which has U inverted. And we can write down the cohomology of M. It's going to be computed by an explicit complex. And in this case, I'm going to use a variant using a psi operator. But speaking, -1, taking invariance by prime to P subgroup. Well, I should say that this is all assuming that P is greater than 2. Sorry about that. And the cohomology of the deformation of M is going to be given by, well, we've got, by passing to the universal deformation over the Iwasawa algebra, we've gotten rid of this gamma action, and now this is just going to be the cohomology of the psi -1 operator. So having, given this built up to explain why we wanted to consider determinants of complexes, we've now put ourselves in the situation where we don't have to think about determinants of complexes. We just have to compute the determinant of the single operator. Okay, so okay, so now we're going to specialize to the situation that I talked about. So M is now going to be rank 1 Bellovin module. And I'm going to, I only need to consider the case where delta of P is some element of it's a unit of A, and this character restricted to ZP1. So gamma is trivial because I've passed up to, I've taken this deformation over the Iwasawa algebra. And so if I want to consider, delta, which are not trivial in ZP star, I'll just do the construction over the Iwasawa algebra and specialize to some other character that's not trivial. We have a side equivariant exact sequence. Describing the Rober ring as an extension of two other modules. So this is going to be functions that converge on the entire unit disk. So there's no, the Rober ring is functions that can have poles I equals 0. This is the subring that doesn't. And this quotient is going to be related to locally analytic functions. So I should say that in this situation, we still have a problem because we want the deformation of M to be, if we want to compute a determinant, we have to be in a situation where we have a presentation which is finite over the coefficients. And the Rober ring is very much not finite over the Iwasawa algebra, even after taking the original analytic generic fiber. So we have to somehow cut this picture down to size to get something finite, to get finite pieces where we can actually compute determinants. So the computations that Nakamura relies on to cut these pieces down to size. So in characteristic 0, so Nakamura uses contends element T in the Rober ring to chop these out to size. But there just isn't, so Fontaine, this element T is closely related to Hodge-Tate weights, and the element and Hodge-Tate weights just don't make sense in characteristic P. So instead, what we do is we shrink spot A so that it's small enough. And what small enough will actually mean depends on exactly what delta P is. It turns out that when P is small enough, we can show that psi minus 1 is invertible in a very large chunk of Q and on this plus part of the Rober ring. And then we get, then again, by multiplicativity in exact sequences, we get the result for over the Rover ring. And then we wanted to move on to something over all of spot A, and then we glue with Nakamura's construction. On the rest of spot A.
Small in the pix prime, like what do you mean is small?
I mean, it's small enough u-adically. So we fixed our pseudo-affinoid algebra A, which is, for example, this ring's power series over U with convergent power series in P over U, and then U is inverted. And so U is now defining the topology. And, you know, the point is that as you get close to the locus P equals 0, P is getting small u-adically. It's a good point. I should write that down. Yeah, so then this operator psi minus 1 becomes invertible on most of Q and its plus part, and we get the result we wanted over for the Rover ring. Okay, so that's the determined topology. And in this rank 1 case, I should also note that delta, this second part of delta, delta A2 of M is canonically equal to A. And so we're done. And then yeah, so we got the rank 1 case, and then for triangular families, we can just take the product of these epsilon isomorphisms for the rank 1 cases. Okay, so I'm out of time, so I'll stop here.
Very much for this interesting talk. Are there any questions?
Why you require a restriction of relatively quantity sugar?
I'm sorry.
Why you
It just makes it simpler, and it doesn't matter in the end because we prove a result over the Iwasawa algebra, and we can specialize at non-trivial characters to get other character type.
And so you mentioned that you can get some cases of epsilon isomorphisms over mod P function fields from this.
Mhm.
Can you uniquely characterize just in the mod P world something that they have to be compatible with? Or if you had two different liftings to a pseudo-affinoid algebra of the same thing over in the special fiber, would you necessarily get the same epsilon isomorphism, or is it?
Sorry, you're saying given row 1 and row 2 from gal QP to FP.
Yeah, to FP double brackets U. Or maybe given two things valued in a pseudo-affinoid that have the same reduction into FP double brackets U.
Sorry, I'm a little bit confused about. Are you asking about this?
Let's say we have two things valued in some pseudo-affinoid, which had the same image in FP double brackets U. Would we necessarily get the same epsilon isomorphism for?
So you're thinking of A as some mixed character pseudo-affinoid, and you're reducing mod P.
Yes.
And you're assuming both the reduction is triangular.
Okay.
So, I mean, so short version is I don't know. Maybe the longer version is that one of the nice things that happens if you're doing, characteristic P triangular and P gamma modules is that there's a lot more rigidity, and that's a consequence of like T not existing. So it makes it harder to compute some things, but it also means that you have more rigidity, and you have, I think you have like you have no fake triangulations. I think you have, if you're triangulating, you have a neat triangulation. But I don't know about deforming that into characteristic 0. That's what you're asking.
This original conjecture excluded the case of function fields, like it's periodic, like his conjectures are for the coefficients and GQP.
Mhm.
Like you given some cases like something over function fields, for example, caret. Is there some sort of maybe does it shed some light on formulation of
I don't know. So I think more not to stand there. Yeah, I mean, I think that the question of how, for example, we're only saying something about triangulin characteristic P representations with coefficients in function fields. We're not saying anything about like the, the non-finite slope or cases at all. But I think the questions about, for example, the distribution of triangulin points in the characteristic P fiber are quite interesting. You have a Galois deformation ring. In a lot of cases, you know that triangulin points are dense in the characteristic 0 locus, but I don't know what the characteristic P story of that looks like. I would certainly, like, I'd hope that you'd have some density segments, but you don't have like crystalline points to grab onto the way you do in the infinite Fern arguments in characteristic 0. So yeah, I think it's a really interesting question.
Any further questions? Well, if not, let's thank Rebecca again.